Hi everyone, hope you're all keeping yourself safe. It's now time for our next instalment on our semiconductor journey, where we're going to be looking at the N junction. So learning intention: to explore the N junction, and our success criteria: I can describe the difference between an N and a P-type semiconductor. I can use the terms forward and reverse bias correctly. I can explain the operation of LEDs and solar cells. So semiconductor bonding. Now we looked at this last time, so I'm just going to bring up that same diagram that we started with. So here what we've got is we've got our positively charged nuclei, and they are surrounded by four atoms. Four atoms in that outer valence band we're looking at here. So we're ignoring all those filled bands that were kind of further down, those filled energy levels. We're just looking at this outer valence band here, where we're going to have 4 electrons. So that outer shell, that valence band, is full for each of these atoms. Each of these has 4 in its outer shell, and that's what is allowing it to join on with these others. That's why we've got 2 here. So it kind of essentially is sharing an electron almost. So there's 1 electron from here and 1 electron from here, they kind of share that little electron. It's the same with all these other nuclei here. Now, just to make this a little bit more real for us, I'm going to give you an example of a type of atom we could be looking at just now. So this could be our type of semiconductor. So this is like a silicon nuclei. Okay, so we're looking at kind of silicon atoms here. Silicon being a semiconductor, obviously. This is like a silicon nuclei, and obviously our black spheres here are our electrons still. So last time we talked a little bit about adding an impurity or impurities in semiconductors and how that can help them to conduct electricity. Now, I think I mentioned as well that we can add an impurity to it. We talked very, very briefly about that. We're going to look at that in a little bit more detail today. So when we add an impurity, we call it doping. And the first one we're going to have a look at is the P-type semiconductor. And we basically make our P or N-type semiconductor using doping. So as I've said, we've got our silicon nuclei here. All of these little red spheres here are our positively charged silicon nuclei. We've obviously got all these little electrons here. Now, what happens if we change one of our nuclei? So if we change one of our atoms and make it, let's say for instance, indium. Okay, different atom, we add indium in here. Now, that seems okay. What's the big deal with that? Well, the problem we've got with indium is that that outer shell, that valence band, is no longer full. So we end up with a little hole in our outer shell. So you can see here, we've now lost that electron there. So we have a hole left in its place. And as I said before, that hole is free then to move around the semiconductor material as so as we've moved the hole's moved from here to here. It could continue its journey. It could move round here. It could move round here. It could move straight across. It could rejoin this atom. It could move up to one of these atoms, to maybe this atom here. It can move around that kind of semiconductor. And because that's free, it's allowing us a little bit of a movement in the way of charge, which is very useful. So this is a P-type semiconductor. So most of the conduction in P-type semiconductors takes place through the movement of positively charged holes, okay? So that's how I remember it, just P positive, simple as that. It is very, very easy to remember if you just remember it in those terms, excuse me. So if you look at the N-type semiconductor, so we're going to stick with our silicon nuclei, okay? So we've replaced all of those with just silicon nuclei again. Okay, so we've got rid of our indium there. This time what I'm going to do is I'm going to replace that atom with something else. I'm going to replace it with an arsenic atom, okay? So now we've got our semiconductor doped with arsenic. Now, like previously, the arsenic doesn't have the right number of electrons in that outer shell. So what we find is we end up in this case with an extra electron. So this little extra electron here, this extra electron again is just free to move around the medium, and as it moves around the medium, it is able to obviously kind of take the charge that it's got with it. So it kind of moves around, and that's kind of what is going to allow the current to flow in this case here. Okay, so that's the two different types of doping that we've got. We've got the P-type and the N-type. So most of the conduction in the N-type semiconductor takes place through the movement of the negatively charged electrons. So again, I've kind of highlighted this in blue. I did it in red in the last slide. N, and negative, N-type, negative. Again, nice and easy to remember. So, why is this useful? Well, they become incredibly useful when we put these two types of semiconductor together. So these two doped semiconductors together. And we do that, we create what's called the PN junction. So the PN junction is basically when a P-type and N-type semiconductor are layered together. As I say, we call that the PN junction. So it looks a little bit like this here. So we have on the left hand side there the P-type semiconductor. On the right hand side we've got the N-type semiconductor. And then in the middle we've got that little blue section there. We call that the depletion layer. I'm going to talk more about the depletion layer in a little minute, okay? But that's called the depletion layer. So obviously with the P-type semiconductor we've got all these holes which are free to move around. And in the N-type semiconductor we've got our electrons. So these are our charge carriers. So the holes here in the P-type semiconductor are our charge carriers, and the electrons here in the N-type semiconductor are our charge carriers here. Now the depletion layer has no free carriers. There's no free charge in there. So no free charge carriers in that depletion layer. Actually it forms a potential barrier. It actually kind of stops the electrons from kind of flowing over and combining with these little holes here, which would obviously then kind of, they would end up cancelling each other out in that case. So we end up with this kind of depletion layer which kind of stops that process from happening. So if we bias the diode, well, two types of biasing, but basically all we're doing is we're applying an external voltage or an external potential difference to it. So two types of biasing. Firstly, we've got forward biasing. So a little diagram just to show you how that looks like. So we've got here a cell and it's hooked up to our PN junction. Now I've just used this to represent my PN junction just now. I will be introducing the proper symbol for a kind of PN junction shortly, but this just kind of helps you to kind of see exactly what's happening. So we've got the negative terminal of our cell connected up here to the negative terminal of the PN junction. We've got the positive terminal of the cell connected up to the positive terminal of the PN junction. And that's what we call forward biasing. So as I say, positive terminal to the P-type, negative terminal to the N-type, and that allows our PN junction to be what we call forward biased. I'll talk more about what forward biasing actually means just in a little minute. Reverse bias is the other one, we need to be aware of. So you'll notice here that we've got exactly the same circuit with the exception of the cell which has been flipped around. So this time our negative terminal hooked up to the P-type semiconductor and the positive terminal hooked up to the N-type semiconductor. So positive to N-type, negative to P-type, okay, and that's how we reverse bias our semiconductor. Again, I'll talk more about reverse biasing just in a little minute, but let's come back to forward biasing first of all. So if you want to forward bias our diode, what we do is we've got obviously our circuit as we saw there. We have the cell here with the negative terminal hooked up to the N-type and the positive terminal hooked up to the P-type. Okay, we have our little charge carriers here. This is our holes. We have the electrons here on this side, our charge carriers in the N-type. And what happens if we have our PN junction forward biased, so if we have it hooked up like this, then the electrons flow in that direction, the holes flow in the opposite direction, and it allows the flow of current in this circuit, and that's an incredibly useful thing. So when forward biased, the cells provide the energy required for the electrons in the N-type semiconductor to almost break through that potential barrier caused by the depletion zone, and then obviously the holes, as I say, move in the opposite direction because of that same process. The diode, and this is actually the kind of a proper name, or one of the other names that we'd kind of call this PN junction. The diode in this case is now able to conduct electricity. So I probably should have said that already. A PN junction is basically a type of diode, or is a diode. Diode is a type of PN junction. It would be a better way of saying that. So let's look at the other side then, reverse bias. So back to our circuit again, we have our cell has been flipped, so the negative terminal hooked up to the P-type, the positive terminal hooked up to the N-type, and of course we've still got, when we do this, what we actually find is we increase the size of this this depletion zone, so that kind of actually almost stretches in size. It becomes much bigger. So of course you've got your holes in here and you've got your electrons here. Because we've made this depletion zone bigger, it makes it even harder for the electrons to move or to flow in any direction, and it makes it harder for the holes to move in the opposite direction. So we're essentially making it harder for current to flow in this circuit. So when reverse biased, the potential applied by the cell causes this depletion layer to increase in width, creating a bigger potential barrier and holding the electrons and holes in place. Okay, so almost no conduction can take place in this set of circumstances. So current flow in a PN junction. Well, let's look at our PN junction. There's our PN junction. We'll just go back to this kind of a model of our PN junction. So obviously we've got our P-type here. I've just labelled that P just to highlight that for you. And this one is our N-type, obviously here. The correct circuit symbol, I told you I was going to introduce you to the correct circuit symbol for the diode. This is the circuit symbol for the diode here. Now, just to make this clear, the P-type corresponds to this side of the diode. The N-type corresponds to this side of the diode. So what we have is, in this circuit here, the current or the electrons are always going to flow in this direction here. Okay, so the current flows in this direction, so it's flowing in to the N-type and towards the P-type. So from the N-type towards the P-type. And this one here, this always used to confuse me when I was kind of first learning about this. It used to always confuse me because I used to always think this looked a bit like an arrow, and I would kind of think, well, surely that arrow must be pointing in the direction that the current's going to flow. It's not an arrow, it's a triangle, and we're looking at the current going in the opposite direction. So it starts at the line and it goes through the triangle there. Okay, just one of these things you're going to have to remember, I'm afraid. So in most cases, the PN junction or the diode will only allow current to flow in one direction around the circuit. Incredibly useful component from that point of view. Now, there's two things that we need to be aware of, or two applications that we need to be aware of. The first one is the light emitting diode. You'll be familiar with light emitting diodes, LEDs. You'll have seen them obviously in a wide variety of components. So we're going to look at that first in a wide variety of appliances. So this is our circuit symbol for an LED. And obviously an LED is a type of diode. So we start off with the basic diode symbol, and then we've got these two little arrows which just represent light being given off by the LED. So the light emitting diode, or the LED, are a type of PN junction, basically. It is as simple as that. So an LED is just a type of PN junction. So how does it work? Well, when the potential difference is applied, electrons are able to move from the N-type to the P-type, as we discussed already. When they get to the P-type, what happens is they actually drop down from the conduction band into that valence band, and in the process they give off light. We'll talk more about that in the next unit. It's actually basically it's a photoelectric effect for those of you that have looked at that kind of side of physics before. But it's essentially the same kind of process there. The electrons drop from one energy level to another energy level, and that energy obviously has to go somewhere. So if there's energy lost by the electron, that energy has to go somewhere. You'll remember from previous physics that energy can't be created or destroyed, so that energy is emitted as a photon of light, and that's how we get light out of an LED. The solar cell. So solar cell is the other application we need to be aware of. So here we've got the symbol for a solar cell here. So a solar cell produces a potential difference when photons of light are basically incident on or when they're absorbed by the solar cell. We call this the photovoltaic effect, just if you're interested. So basically what happens is the energy is absorbed, so the energy from the photons is absorbed by the semiconductor material, by our PN by a solar cell, sorry, and it causes the electrons to jump from the valence band to the conduction band. We talked about that back in the last lesson, about a way of being able to cause a semiconductor to conduct electricity. Light was one of the ways that we were able to do that. So that's exactly what we're utilising here, where we're causing that light to jump from one energy level to the next, and we end up with electrons in that conduction band. Now, because this is a PN junction, or because we've got a PN junction in here, what happens is these electrons will then move towards the N-type semiconductor. And when you're kind of pushing those extra electrons into that N-type semiconductor, what you're doing is you're basically creating a potential difference between either side of your solar cell. Because you're going to have your kind of holes on one side, and you're going to have all these extra electrons now in your N-type semiconductor. And that's essentially how a solar cell works. You then get that potential difference across there. You can use that potential difference to provide you with the energy that you need to run some appliances. Depending on how big your solar cell is, how big your potential difference is, you can run sometimes some quite big appliances from a solar cell. So that's it for the PN junction. Okay, now I have gone through that quite quickly. I'm very well aware. I'm going to find you a couple of questions on the kind of semiconductor stuff to have a look at. I'm just going to pick out some past paper questions because I think it's kind of quite important. We just have a look at some past paper questions. And what I'll do is I will put a note of those past paper questions on Google Classroom, so you know what to do. I'll probably get you to submit those. Either take pictures if you're doing it on if you're doing it on paper, take pictures of it and submit them, or maybe in a Google Doc. I'll get you to kind of put it into Google Doc. And kind of submit it that way. The good thing about the semiconductor stuff is, at this stage at least, there is absolutely no calculations that we need to do. It's just all remembering. So it's just all the facts that we need to remember that you've covered so far. So I'll put those questions on Google Classroom. But before we finish, let's just recap on our success criteria. I can describe the difference between an N-type and a P-type semiconductor. I can use the terms forward and reverse bias correctly. I can explain the operation of LEDs and solar cells. Hopefully you're able to do all of them well now. In the meantime then, keep yourself safe. Hopefully middle of February we'll maybe get to see each other again in person. Who knows at this point in time, but until then, keep yourselves safe, guys.